Okay, thanks. All right, thanks everyone. I'm excited to talk about our CLPS selection, which is a small ion trap mass spectrometer. We propose this to be able to look at the native lunar exosphere, especially in response to stimuli like landing, and I'll talk about some of the expectations that we have for this. I did want to make sure to my OU colleagues acknowledged support from the European Space Agency and the UK Space Agency, and of course we are funded by the NPLP program. I don't need to tell this crowd this, but there's water on the moon. There's a couple different sources of water on the moon, and we don't yet know whether or how they are related to each other. And so I think whenever we put up this slide, we always just say more data are needed, so let's go get some more data. Mehdi Bena had this great paper with LADI results that really brings into focus this lunar water cycle, and that's what we're really after here. So if you haven't read this paper, you really should. It's really pretty great. And so they proposed a possible mechanism for how lunar water makes it into the exosphere and what happens when it bounces around. Based on what you can see from LADI, which was in a 50-kilometer orbit. 50 kilometers, 100 kilometers? Something like, it was, yeah, lunar orbit. So here, the main driver for this surface correlated water is the solar wind brings in hydrogen. You've got rocks that have 50% by weight oxygen. Those two things combine and make these water molecules. So the solar wind imprinted hydrogen is you can think of it as an exogenous source, right? This is creating water on the moon, and that water can then be sequestered in the hydrated layer or lost to the surface. So you end up with this sort of desiccated layer here where you're losing you're liberating water molecules by micrometeorite impact. So every time you're doing that, you're liberating these molecules. They can hop around to another place. They can go back down into this deep reservoir, or they can be lost. But ultimately, when they looked at the abundances involved and what they could see with LADI, what they concluded, and this is important, is that there has to be some kind of water reservoir at depth to be able to do this resupply. If you add up all the micrometeorites that are hitting the moon over time and how much you would be liberating, that supply, you'd have to have a resupply in order to see what you see with LADI at the present time. So in order to test this, we really need to have multiple measurements in multiple locations at multiple depths. That's really what we would like to do to see whether we have a lunar water cycle. But there's a limit to the kinds of missions that something the size of LADI, the size of the neutral mass spectrometer that was on LADI can fly on. Goddard mass spectrometers, since I've been at Goddard, I'm super impressed with the Goddard mass spectrometers. They're really excellent planetary science workhorses, and we really like them. But, 11 kilograms and sort of 40 centimeters on the side is not something that you're just going to put down lightly on the surface. And so our idea, and I should actually acknowledge Mehdi has also an NPLP funded instrument that takes some I don't want to say spare parts, but some flight parts from different mass spectrometers and puts them together, and it's a very similar outcome to ours. So we're at least getting two in different places. We're flying on different landers, but I think there's a reason to have multiple mass spectrometers on the surface and probably in orbit too. Okay, so our particular instrument is called PITMS. It's a terrible name. I spent a lot of time in graduate school coming up with names for things and cool acronyms and funny acronyms, and most of them were probably really inappropriate, which is why none of them actually made it. And then I wrote this proposal so fast that I didn't have a good name. It still doesn't have a good name. It's called the Prospect Ion Trap Mass Spectrometer, and the reason is because it's derived from the Prospect payload that ESA is developing for Luna 27, the Russian rover. So this is a partnership between ESA and Russia for Lunar 27, and this Prospect is a payload element that's an add-on to the side. So here's Luna 27, the lander, and here's the Prospect package that's sort of hanging on to the side here. And this package is made up of three things. It's got a sampler, like a drill that samples. It's got an inlet system. This is similar to what you might see on Curiosity on SAM. And then it's got ProSPA, which is an analysis package. So it's got a GCMS, it's actually got two MSs, it's got an ion trap mass spec and a magnetic sector mass spectrometer, and a whole bunch of other things that are in there. This is not to scale. This is the ion trap mass spectrometer that fits inside here. So I knew about this. You've probably seen this presented at a couple conferences. I knew they were developing this ion trap mass spectrometer. And I called them and said, hey, do you have the flight model of that or the engineering model of that? Could we fly it in the CLPS program? And they said that would be great. Well, it turns out that this Luna 27 has been pushed out a little bit, so this flight development is a little bit delayed, so we're going to be leading that. So we're going to be making this mass spectrometer from scratch, but it's entirely based on this design. The design is already done. There's no development that has to be done. They already wanted to build this anyway. And this, in turn, is based on the Rosetta mass spectrometer that OU built and flew successfully. Rosetta maybe wasn't as successful as we wanted it to be, but it did touch a comet, and it did take spectra on a comet, mass spectra on a comet. And here's just two examples where you can see well-resolved mass spectra from 67P. So this was in passive mode. Right here you would be in active mode. I put a sample in here, I heat it up, I measure the gases that come out. This was in passive sniffing mode, which is not really how it was designed, but everyone was pleasantly surprised that it can just sit there and sniff whatever is around and get a really good measurement. And so that's what made me think of it, and Simi and my co-PI agreed that just putting it in sniff mode would be a really great thing to do on the moon. So that is what we're doing, and it's very friendly to small landers with a small envelope and a small resource consumption. So here's what it's going to look like when it's on the CLPS lander. We are manifested on Astrobotic. Oh, I talk about the next one. So here's what it looks like. Here's the ion trap mass spectrometer and the electronics. So OU is just building this as is. Here's the ion trap and here's the electronics, and that's going to come as a single package. The idea here is that we are just taking what they have for their mission. So we're not making them do any design. We're not making them do anything special for us. And we, Goddard, are taking on the responsibility of integrating that into the lander and the CLPS program. So you see this kind of adapter. It's not really a lot of engineering. It's just an adapter plate that fits to the bolt holes of the lander. We do need a baffle so that we are not just sniffing the lander itself. And we have an inlet cover so that we are not blowing dust into it as we're landing. So that's just a pop-off cover. So then the whole thing is going to end up like this, and then we're going to wrap it in MLI. So it's a nice little simple device. We were manifested onto Astrobotic, onto their Peregrine Lander, which is super awesome. We're going to Lacus Mortis in 2021, which is a big Mare surface. At this point, any surface measurement's a good measurement. It's near equatorial, so it's somewhat comparable to LADI. The whole mission is 192 hours, so it doesn't give us that long of a time. It doesn't give us a full diurnal cycle. It's only during the daytime, so we don't get a sort of night terminator passage. It's going to be a very simple operation. We're going to blow the dust cover as soon as we get a landing signal, and then we are just going to passively integrate until everyone is dead. So we're just going to sit there and scan. We can co-add on board, or we can bring all the data down and co-add it to get better signal to noise. That sort of depends on the exact method of the data download. But what we expect to see is the decay of the interaction of the lander with the surface. And anything that is a transient event we expect to be able to see. Probably we're going to see a lot of outgassing from the lander and the payloads itself. It would be nice to be able to link it to external stimuli if anything touches the surface. We don't have any specific plans to do that ourselves, but certainly we're going to work with the other payloads. And I'll just put in a pitch here. Every lander contaminates the atmosphere and contaminates its surroundings, so it would be great to have one of these as like a little monitor if this works. on every flight. Maybe it's not us. Maybe I'll make the case that it's us, but it doesn't have to be us. Just having a mass spectrometer would be super helpful. Having it in different places to really pin down this volatile cycle. So latitude, leading trailing hemisphere for that micrometeoroid flux, and dependence on the diurnal cycle. We really do want to see the terminator crossing, see what happens at night. I think those are really important parts of the story. And mass spectrometers in general are a workhorse of planetary science, and they can do so much more than exospheric monitoring, as important as it is, and as much as I'm going to enjoy doing that. Active experiments where we disturb the soil or we ingest a sample and want to look at volatiles that are contained within the sample, those are really important. Mass spectrometers, of course, are a key part of in situ dating, so I'm excited to test these out and make sure that we can do these things on the moon. Thanks.
Great, Barb. Any questions?
No questions.
Is there any chance that you can operate this in ion mode?
No, not the way it is now. Yeah, there are ways you could do it in the future, but we're trying to just keep it super simple.
So I have a related question. There are soft ionization techniques that are available so that you can actually get the molecular information rather than the high energy electron impact. So is Mady or somebody going to use some soft ionization so that you can get more information than just the simple volatiles that are there?
I wish I knew more about Medy's instrument so I could tell you that, but I don't know the answer. Sorry.
Barb, do you think, let me ask you a question myself, do you think that, what are the chances are of measuring the native exosphere relative to the lander plume? Have you?
Bill, you're a co-I for the reason of thinking about this.
Well, boss, I need help.
I think we should calculate that. What do you think? All right, let's do that.
Okay, so this is, I clearly got myself into some trouble here.